Dzień dobry. That's probably the last Polish word I'm going to say during this presentation. Welcome to Deterministic Systems, Why and How To. My name is Rafal Foltynski. I was meant to be joined by Nick Palmer today. Unfortunately, he couldn't make it, so I'm going to do it alone. If you have any questions, visit the QR code and you know what to do. All right, who am I? I'm Raf. I'm an open source contributor. I'm running a project called Log4j to Elasticsearch. Highly encourage you to have a look. Also made a few contributions to Jackson Core. I've been a Java dev for 13 years. I've been in LMAX for over 4 years. But it's not only about code. I also have some hobbies. If you'd like to jump out of the fully functioning airplane with me, come over to UK. All right. Opinions expressed here are mine, not LMAX. This is a talk about deterministic systems. But given the nature of the topic, given the numbers and theories I'm gonna present, some context is important. So, what is LMAX? Well, we are a financial exchange. We are a leading operator of multiple institutional execution venues for FX and crypto. Unlike Coinbase or Binance, we are oriented towards mainly institutional clients. Banks, brokerages, professional traders, people with big wallets who really like the features that we provide, namely strict price and time priority order execution. One of the main topics of our talk, and performance. What we are offering to our clients is a round-trip latency of around 80 microseconds. Anyone doesn't know what a microsecond is? 1,000th of a millisecond. So we can handle peaks up to around 800,000 orders per second. 100,000 sustained. 100,000 orders per second is a regular BAU. This sort of traffic can generate millions of inter-service messages. So now you're wondering, how do we deal with that? Why are we here? Well, I hope that I will be able to prove to you that deterministic systems are good, that concurrency is hard, and that we care about performance. So, what is a deterministic system? I'm based in London. The first result in Google says that determinism entails that in a situation in which a person makes a certain decision or performs a certain action, it is impossible that he or she could have made any other decision or performed any other action. This does not apply to systems. If you replace person and he or she with system, that makes a bit more sense. However, there's a bit better definition from Technopedia. A deterministic system is a system in which a given initial state or a condition will always produce the same result. There is no randomness involved or variation in the ways that inputs get delivered as outputs. You can execute those inputs millions, billions, trillions of times. You should always produce exactly the same output. So, what are the benefits of a deterministic system? One of the benefits is simplicity. If you design your system well, if you design the way your data flows throughout the system, the architecture will become quite simple. Your code will become simple. Your system will be very, very, very easily debuggable. Since a deterministic system will behave exactly the same any way you run it, you can easily take whatever state you had in production, run it on your local laptop, run it on your laptop or your local computer, and you will reproduce exactly the same behavior. It's fairly easy to fail over if you do it right, and ultimately, if you do it right, you're going to achieve extreme performance. So, how would a non-deterministic system look like? Imagine that you have two APIs, payment API and order API. And there is a user that would like to execute a withdraw operation on a payment API and buy more operation on the order API. And his balances gives him just amount of cash to execute buy more. Also, you have an account service with some sort of balance and some sort of threat pool. If a client executes a withdraw request, and this command will get executed in the account service, this shall pass. If he executes buy more on its own, it will be fine. It shall pass. However, if the client decides to execute both operations at the same time, and your threat pool decides to execute those operations concurrently, what will be the effect of how would it affect the balance? If your company is in the money-making business and these two commands will execute at the same time, you may end up with negative balance. One of those commands may fail. Hopefully one of them will fail. If they don't, and you're in the money-making business, you will not be on the market for too long. So, how to spot opportunities for a deterministic system? If the ordering of your commands is important, take account balances, very good example. Any sort of system that has to store accounts like booking, any sort of booking systems. And whenever you update your state frequently, and you already noticed that you have some issues with concurrency and concurrent updates because you have a lot of pain in production, you may want to think about turning your system or service, part of the system, to a deterministic one. So, how to put it into practice? Well, TLDR, if you're really short on time, note those three statements. First of all, you need to record all of your inputs. Everything that comes in, everything comes into your system. Every command that gets executed in your system must be recorded. You need to update your state with only one writer. There should never be a situation where two threads or two actors change your state at the same time. Also, you cannot do anything that you cannot reproduce. Otherwise, you will not be able to reliably restore and reproduce the output anywhere else. How would it look like? Imagine you have a thread, a single thread, that changes the state. Doesn't matter what changes. It can be increment, can be whatever. In order to execute commands one by one, you could use a queue, a buffer. You take the first element from your queue or buffer, execute the change, produce an output. You take inputs commands in order, you produce outputs in order. But do we have to use regular buffers? Well, I work in LMAX. LMAX a decade ago released a library called Disruptor, which is a concurrency library that allows you a small concurrency framework, a library that allows you to execute a high-performance exchange of messages between two threads. However, it's much more than a ring buffer. A lot of components of this router allows you to orchestrate the way your events are consumed, control the way your events are published to a ring buffer. And version 4 was just released. Enjoy. What are benefits of ring buffer over a regular connection? Well, regular queue. Well, regular queue is ordered. Ring buffer is ordered as well. Ring buffer provides you with very nice mechanism for sequencing of your reads and writes. You can also easily access previous elements. you don't physically take your messages off the ring buffer. They stay there until you wrap. So when we come back to the previous slide, we can easily replace our queues and buffers with ring buffers. And again, we consume next message one. We consume messages on the left one by one. We publish it to the ring buffer on the right one by one, and change our states in a single thread. But sometimes our buffers can get full. When buffers wrap, we're going to start overriding previous messages. There must be a way to deal with that, right? So what we can do, we can introduce a journal. Before you execute any change to your system, you can write it to disk first. You can store whatever command will be executed later in your system. That sorts out record all incoming traffic point. If it's not journaled, it didn't happen. If it's not journaled, it can never be processed. Also, with a journal, another benefit that you're getting is that you can always replay your journal from. You can always replay your journal to reconstruct your state. However, there is one more problem. There's one problem with this approach. Imagine that you're running your system for 10 years, and suddenly your system crashed. You would like to restore your system as fast as possible. Replaying 10 years of events might take a while. Well, the states, the in-memory states, can be snapshotted. This way, whenever you have to restore your system after crash, you can simply restore the snapshot, replay only the amount of events in your journal to get you to the latest executed command. This way, your recovery will be quicker. Journals with snapshots allow you to easily allows you to fill the gap between the crash and the restoration of your primary system functions. However, in order to record the states, you would have to stop the processing. Okay? Therefore, it's beneficial to do the actual snapshotting on a replica. You can replicate every event that will be executed on your primary to a replica first. And if your system is deterministic, if your service is deterministic, the replica is an exact copy of your primary. It will execute the change exactly as the primary would. If you need to take a snapshot, you can stop the replica first, take the snapshot, allow the primary to carry on, and eventually replica, once you resume the processing, your replica will catch up. How do you replicate? Replicate fast. You remember the point where nothing gets processed before it gets journaled. Also, nothing gets processed before it gets replicated. You can simply send your message over to the replica, wait for a confirmation that sure, yeah, I got it. I wrote it to my ring buffer. I didn't journal. I didn't do anything else. I just put it in my ring buffer. Send the message back to your primary saying, yeah, I'm okay to continue. Replica does not accept any other messages apart from messages from primary. Otherwise, it also doesn't produce any results. Otherwise, on the other end of your processing, you would get duplicated messages. So Primary always consumes messages, consumes commands to execute, always journals, always replicates. Replica always stores messages in the ring buffer first, then both of them will execute journaling. Replica can execute snapshot, can execute creation of the snapshot. And it should be, if you do it right, it should be fine. One problematic bit is how to migrate these kind of systems. Whenever you have a change in your in the way you store your events, whenever you change the format of your events, add new fields, you might need to migrate your snapshots to a new version before you can bring the service up. Also, it's much more preferable to rather introduce new events or new versions of events rather than modifying the old one. Otherwise, you might also want to migrate all of your journals, which, given the potentially long lifetime of your system, might take a while. Also, whenever you replay any of the old journals, please make sure that you do it with exactly the same version of code you created it with. So, are we deterministic yet? Well, we can compare our snapshots and find out. Imagine a time frame with T0 where you take a snapshot file sometimes past. You produce another snapshot. You can create a copy of your first snapshot, and you have a journal, and you know that if your system is deterministic, the second snapshot you produce after you replay your journal should be exactly the same. They should be binary equivalent. If they are not, you're probably not deterministic. What are the common pitfalls with this approach? How can you fail to write a properly deterministic service? Well, you should probably avoid unordered collections. Imagine trying to write a snapshot. Imagine trying to write a hash set. Whenever you create an iterator of a hash set, it will most likely never retain the order you put your items into your hash set. Try to avoid wall clocks. Whenever you accept the message into your system, and you just take a system time, then whenever you replay it on your local environment, and you will also take local environments time, the output will be different. You're going to produce different timestamps. Try to avoid any sort of external queries. The database, any database queries, any RPCs to an external service, that's a big no-no. These things change. Whenever you need to insert anything into your system, whatever data you need to put in your command must be ready before you know what to execute, right? Otherwise, it will massively slow you down and produce non-deterministic results, because databases, external services are changed by external actors. Try to avoid any sort of randomness. If you have to use random, use a seeded one. Avoid creating any sort of configuration changes between your environment. This may and will affect the way you produce your outputs. So, again, what are the benefits? With this approach, ultimately you're going to gain simplicity in your code architecture, the way your data flows through the system. Debuggability, you will always be able to take a copy of your journal and snapshot, restore it in any environment, and figure out exactly what happened. It gives you some level of resilience. You should be able to always fail over to your replica and continue to operate until the primary is back. The behavior is predictable behavior. This is a very good benefit in a single threaded system where you don't have any sort of concurrency, and you don't execute our commands with any sort of non-determinism or any. The order of execution is very, very much predictable. Ultimately, you might also achieve tremendous performance. In the TLDR, I wonder how much emphasis, how much attention you put to this sentence. Only updates your state with one writer. I would actually ramp it up and say only update your state from one thread. But why? Concurrency is hard, dear folks. So, when you look at this code, this is simply a code that tries to increment the variable. In this case, it's atomic long. It could be executed a bit easier. However, it very well represents the usual pattern of how you work with your regular services. You're checking the current state, and then you execute your updates if the state allows it. In this case, if you execute this code in multiple threads, do you think it will be thread safe? Is this a thread safe update? Well, we can check whether it is. Anyone knows JC stress? There you go, there's one hand. Good. Any more hands? All right. JC stress is a Java concurrency stress library. It allows you. It's a Java. It's a framework that allows you to check whether some small piece of code can be executed by multiple threads, and does it produce the outputs you expect. Notice that the outcomes that are defined over there, they are not duplicated. All of them are acceptable. I guarantee that once you remove any of these outcomes, this test will fail. What I would really expect from a deterministic system is that I'm only going to get 1, 2, 3. So I think that we can easily say that this code is thread safe, but it's not deterministic. So yes, concurrency is hard. And also, 2 threads the faster, right? And 4 threads the charm. I created a framework. Well, sorry, created some small repo with a few JMH benchmarks that can tell you how fast you can execute a plain update, volatile update, and also use any other synchronization methods to ensure safety of your updates. Notice that whenever you go beyond 1 thread, the performance drastically drops. I would say that it depends on your workload, right? There are some workloads where you can easily split out some chunks of your data, modify this data concurrently and safely. However, this will not give you this, and it may give you higher throughput. However, when you need to share the state between multiple threads, I would much rather go for a single-threaded execution and a regular plain Java write. In order to execute those safely, I'll reveal the trick in just a moment. So, treat your thread well, because you only have one. But no, some developers might tell me, but I really need the block here. I really need to execute this very, very important I/O operation. Do some, store some intermediate results. Maybe write something to the database immediately. And I always ask them, do you really have to block here? All of your state is already in memory. Change was already executed. You're ready to accept another command. You can simply produce the result, consume this result in another thread, store it somewhere else, execute these I/O operations on another thread, or any downstream service, and it should still be fine. Why is that so important? If you have a single thread, imagine a timeline where you execute a few updates. Those blue, those small blue lines represent time spent on a state update. If you fill it up with I/O updates, you will saturate this thread very, very fast. Once you separate those updates, once you do them somewhere else, and once you pin your threads to CPUs, you will suddenly be able to execute plain write, because the data will always be the data that you're changing. The regular plain Java variable Java field is safe. It's safe to update when you execute it. When you always execute this change on a single thread, and also you will be able to measure how much capacity your system has. And eventually, once you fill one of your threads, once you saturate one of your threads, you will know what is the next area in your system that you have to improve. With this architecture, it's very easy to spot any sort of bottlenecks. And it usually will be the I/O that will take the longest to execute. Once you enforce those, once you introduce this sort of architecture in your system, this solution, you will have no locks on your shared state. You will not have any sort of contention on logs. You will execute your updates as fast as possible without any sort of distraction. Your CPU will execute one thing, one change, and one change only. Will be dedicated to do only one thing. You're going to reduce jitter further if you isolate it. If you isolate your CPUs, you have less topo, you have task set, TUND to help you out with that. In Java, you have the thread affinity from Chronicle that can help you out with pinning threads in runtime. What is jitter, you might ask? Well, jitter is sort of erratic behavior, erratic latency around usually 4 and 5 nines on your latency histogram. With this approach, you're going to achieve very, very predictable latency, right? Without the 4 nines and 5 nines going crazy and randomly, which is very, 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 very important when you're operating a low latency financial exchange. This is an example output of LSTOPO for one of the AMD processors. Don't worry about the layout. About this particular layout, this changes depending on processes, on the model of processes used. But one thing that is interesting is is, for instance, I know that processor 0 and processor 1 have some network interfaces over there. In some other spots you might notice that you have easy access to your hard drives and I/O devices. This might help you with figuring out which thread should be pinned to which CPU to execute your code the fastest. So, do we know why single thread updates are better? Well, the code is easy to reason about. You will never have to worry while you read your code how many actors, how many threads can execute the update. They will always be executed with only one thread. It's simpler for developer. This kind of code can be made deterministic with ease. Once you pin it, CPU is very happy because suddenly it has one job and one job only. You will get low jitter, very consistent latency. So, I was trying to prove that deterministic systems are good. I think that's check. I tried to prove that concurrency is hard. It is hard. And yes, we do care about performance. And if you ever manage to create a system like this, I'm sure you're going to discover all those 3 points, and eventually you will be very, very, very happy. All right, that's all that I got for you today. If you'd like to see the code, see the benchmarks, reproduce the results, they will vary depending on the CPU and CPU use. But take a look and enjoy. Do you have any questions?
Możesz jeszcze raz ten poprzedni slajd? For half of your presentation, I felt like it was description of event sourcing. Was I right?
In a way,
It's in-memory implementation
Yeah.
of event sourcing.
yeah, in a way it is. It's very close.
And you implement it from the basics, or you use some kind of framework like Akka or
So
something?
no, the only framework that we use is Disruptor. Other than that, we use core Java. In order to go ultra low latency, you cannot use any sort of open source framework. None of the open source framework will give you the performance that you need. You have to you will, if you want to go ultra low latency, you will eventually be forced to write your own code tailored exactly to your needs. Yep. So no frameworks.
Do you write in Java?
Yes.
Why do you started with Java? Because low latency.
I think that one of the biggest factors was the ease to hire new developers. Right. It's quite difficult to hire a team of C++ developers that really know how to write extremely performant code. With Java, you can write some suboptimal code, and JIT will help you out. It's also easy to hire new people.
One again.
Go.
What about garbage collector?
With garbage collector, all right. The question about garbage collector, we use Zing, Azul Prime, which gives you C4 collector. It's a pulseless collector, which theoretically allows you to forget about GC completely. Also, with these approaches, whatever you put into the ring buffer, you're not really creating any new objects. We usually usually use bytes, and we just rewrite them from one place to another. Whenever we have to unmarshal, we may create one object per operation, right? The actual instructions you have to execute. Otherwise, it's all primitives. It's all very, very raw, very, very simple. Yep. So GC is a factor if you use regular JDK, regular hotspot GCs. However, I know a few exchanges that run very, very fast on G1, and they're also happy. However, you need to write very, very specific code to achieve that. Go for it.
But do you try to use epsilon garbage collector for tests?
No. Sorry, the question was about epsilon. Do we use epsilon? No, we don't, and we don't try to use epsilon. We go Azul Prime all the way. There is no point to use epsilon in tests and other environments and then use Zing in production, right? It's right.
Because that would answer to the question: do you really create objects, or do you use all?
Yes. Yeah, we do, but we don't have to worry about it too much. Whenever you start to use Zing, you will cry, because all of the efforts that you try to put into your code to make it low garbage, Zing will sort it out for you. Or rather, it will make you not worry about it that much, because any pauses that you had are gone. We're almost run out of time, so go with your question.
How do you test this circle? Like you make the change to the software, how do you test it to keep this premises of?
Right. How do we make changes to the software? We have a very, very extensive set of tests. It is very rare to reach production where in the state where your deterministic system will be broken, assuming that you will invest massive amount of time in testing, right? So how do we make changes to our system? Well, we try to rely on skills of our brilliant devs, and later on feedback from our CI.
Testing is incredibly important. So, what would you estimate as the amount of time you would spend on testing versus the actual coding?
I would say that the amount we spent on actually figuring out what are the scenarios, how we're gonna affect our system, how we're gonna change our system, how we're gonna accept any sort of configuration changes. This is usually determined before we even write any line of code, right? We heavily rely on cooperation between developers and testers to produce giant amount of test scenarios. Then we start to produce. Then we start to write a code and try to make them green.
Kind of scares me. So let's just say, in a normal environment, I would spend 20% of the entire time on testing. Right?
Yeah.
20% coding, 20% on testing. That's it. So how heavy?
I would
is it?
easily say 80-20.
So 20% coding, 80% testing.
Yeah. Maybe even more.
I think we're running out of time. So Łukasz, thank you very much for your presentation. Speed matters. I think that's the most important thing to remember from today's presentation. Thank you for attending. Have a great conference.
Thank you.